In this video, we're going to talk about the idea of constrained optimization, also known as the method of Lagrange multipliers. So our objective here is that instead of having just some function we want to maximize or minimize, we have some sort of constraint imposed on that function. So to pick a generic example, let's suppose that we want to minimize this paraboloid, f of x, y equals x squared plus y squared. However, we don't just want to find any minimum or any global minimum along the entire domain of the function, but instead we want to limit ourselves to minimizing the function along the plane x plus y equals 10. So in essence, logically speaking, we want to make sure that the sum of our two components that we find to be a critical point sum to 10. So in terms of looking at a three-dimensional function, the way we can think about this is that here's our paraboloid, and a paraboloid, this one we could use the find critical points and do the second derivative test and show that 0, 0 would be the global minimum, but we want to restrict ourselves to only the parts along this plane where the sum of the two components is 10. So if we look at the contour plot, which it's a little bit easier to see, here is again our absolute minimum. We can see that here, but we want to make sure that x plus y equals 10 is also achieved, that's the constraint. And according to this diagram, it shows that this blue line represents the slice of the paraboloid where the sum of the two components is 10, and the 0.55 is that minimum. Now we can also visualize this by looking at the paraboloid, and we can see that this blue glassy looking thing is the constraint, x plus y equals 10. So that's a plane that runs on its edge, and we can see that what it does is it slices the paraboloid and it just limits us to just that particular cross section right there. So it's sort of, we're creating a cross section, but our cross section is not straight on in the x direction or straight on in the y direction, because it's just important that the sum of the components is 10. So basically we can still think about this as an optimization problem, but it's finding the minimum along a parabola. After we've created that slice, we've essentially created a parabola out of that function. Okay, so let's actually see how this applies and why this would be useful. So a neighborhood health clinic has a budget of $600,000 per quarter. The director of the clinic wants to allocate the budget to maximize the number of patient visits, V, which is given as a function of the number of doctors and the number of nurses. So clearly, the more doctors and more nurses we have, assuming our facility can handle having more doctors and nurses, then we would be able to maximize the number of patient visits that way. But we've got this budget, that's a constraint, and a doctor gets $40,000 per quarter, nurses get $10,000 per quarter. So the first thing we want to ask ourselves when we have a constrained optimization problem, when there's a constraint, we want to maximize this, but we're subject to the budgetary restrictions. So what is our objective? Well, it's to maximize the number of patient visits. Okay, what's the objective function? Well, the objective function is given to us, and I'll relabel it as f of x comma y equals 1000x to the 0.6 times y to the 0.3. That's our objective function. That's the thing that we want to make as large as possible, but we've got this constraint, right? What is that? Well, the constraint is we want to use up, and we're going to always assume for simplicity that we want to use up the entire budget, that it's going to be an equal to, not a less than or equal to problem. That creates some more interesting features that we're not going to deal with here. Well, how do we get that budget equation? Well, I know that I'm going to have X doctors, and each doctor gets paid $40,000, so that's 40,000 X total paid out to just the doctors, and 10,000 Y for the nurses. And when I sum together how much the doctors get paid plus how much the nurses get paid, I want that to equal my budget of $600,000. And I'm just going to simplify this, divide both sides by 1,000 just to reduce some of the zeros, and we get 40x plus 10y must equal 600. Okay, so let's explore this first with Desmos. So what I'll do is I'll pop on over here to Desmos, and what I'm going to do is I'm just going to plot the line 40x plus 10y equals 600. And I'm going to type in 1000x to the 0.6, y to the 0.3 equals v, but what I'm going to do is I'm going to insert a slider for the number of visits. And so because this is a multivariate function, the only way I could graph this is if I can get it down to two variables. So I can kind of look at or simulate different v's and see what's going on here. So let me zoom out a little bit. So there's my budget constraint. So what I want to make sure is that if we're kind of looking at this down from the top, pretend that right where my cursor is, that the z-axis is coming straight towards you out of your screen, and we're looking down upon this, and here's our slice. and we're going to get different contours here by changing the different value of v, fixing the value of v, and looking at the relationship between x and y. So just because I played around with this enough, I'm going to go between 9,000 and 10,000 on the number of visits, because keep in mind this is a total number of visits, so we expect a lot of visits out of a few doctors. So I'm going to change this back to 9,000. And so what interestingly happens is right now what I'm seeing is this red curve represents the number of visits that I can get as a function of the number of doctors, x, and the number of nurses, y. So if I want a lot of, if I have a lot of doctors, I can certainly get enough doctors and very few nurses to take care of 9,000 patients, but obviously having a lot of doctors is going to cost a lot more too. Whereas going in this direction, I'm getting, vice versa, a lot of nurses by making y bigger but decreasing x. If I increase x, then I get more doctors but fewer nurses. So here's the problem though. I can't just pick any point along here. I can't make this as big or small as possible because right now the only 2 points that satisfy my constraint is approximately that point right there. 12.6, 9.6. If I have that many nurses and about 13 doctors and 10 nurses, I'll be able to get about 9,000 visits. But the question is, could I get more? Well, if I make this a little bit too large, let me see what happens here. I'm going to kind of zoom in just on that portion there. If I make this too large, notice that now the number of visits that I get is 10,000, but the fact that I am above this is my budget line, 40x plus 10y equals 600. The fact that there are no intersection points between my slice and my contour tells me that that's not going to be possible for me to get 10,000 visits. So the question then becomes, I can keep moving this thing, right? And the higher I get v, the better. So as long as I still have intersection points between my budget, satisfying both my budget and my number of visits equation, then I can satisfy these. So I can now have about 12 and 12 roughly doctors and nurses and get 9,410 visits. I increase it a little bit more. I still have possibilities here, about 11 doctors, 16 nurses will get me about 9,610 patients, or I could even do 8 doctors and about 25 nurses roughly. But I can continue to increase this until I get no more intersection points between my budget equation and my my visits equation. So here I could still achieve about 9,720 patients, but hopefully you can see what's happening here. At this point, it's impossible to get 10,000 visits because it's going to put me way over my budget. It would require way too many doctors. For example, I could have roughly about just about over 10 doctors and about 20 nurses. I could get about 10,000 visits, but I can't afford it because it would require me to have a higher budget. So I can see that if I take a look at different values, let me do this. I'm going to insert a table, and I'm going to put in, this is going to be the number of doctors and nurses, and I know that my budget is 40x plus 10y, and I'm going to try different combinations here. So for example, right now I'm claiming that I can get 10,000 visits, but I'm going to be way over my budget. So for example, let's pick a point that's roughly an integer value. We'll say that's about, let's see here, kind of hard to find them. So this point is roughly around 10 doctors and 22 nurses. So I have 10 doctors and 22 nurses. Then I will require a budget of 620,000, which is higher than my allotted budget. If I pick 10 and 21, that is, I can achieve that by getting 9,920 visits, but it's still going to put me $10,000 over budget. The only way I can hit it about exactly is where my number of visits curve and my constraint curve touch basically at just one point. So it appears that, I can keep zooming in here, but around 9,780 visits, I can achieve that by having, well, let's see, it's kind of hard to tell exactly where these things are intersecting, but I'm just going to eyeball it. So around 10 and 20 appears. If I have 10 nurses, or 10 doctors and 20 nurses, I'm dead on my budget, $600,000, and I've been able to maximize the number of patients, any more than that, and suddenly I'm requiring a larger budget than I have. So this is the idea of constrained optimization, is I want to find the biggest possible output that I could get, provided that I meet my budgetary constraint. So what we did here is we plotted the constraint equation for 40,000x plus 10,000y equals 600,000, or really 40x plus 10y equals 600. And then we also plotted v equals our visits equation, letting v be a sliding value, try to make it as big as possible with there still being an intersection between our constraint and our number of visits equation. So we got around 9,780 total visits, and that required about 10 doctors and 20 nurses. That was that point right there. Okay, couple things that we need to notice is that f of xy is maximized when g of xy equals 600,000. So g of xy is our function 40,000x plus 10,000y. That's our g of xy, and it was set equal to a budget of $600,000. When f of xy, or excuse me, when g of xy is tangent to that function. So if I back up here, we can see that my g of xy function, this red function, is exactly tangent to the blue curve, and that appeared to be the case where our function was maximized. Well, we're going to go with that. That's just kind of some of the intuition behind it. And one other thing that we're going to claim here is that when that happens, the gradient of f at this point of tangency points in the same direction as the gradient of g. So we get into gradient conversations here. Now, so the gradient of this guy and the gradient of this guy, we're arguing, point in the same direction. We're not going to prove that here, but if you think about where the gradient points, it always points towards the direction of maximal increase in the surface. And if I come back here once again, notice what's happening to my g of xy. It's always traveling out away from the origin, right? That's traveling out away from the origin. And if I increase the budget, if I increase this to 610, notice where it's going to move. It's going to move out away from the origin as well. So notice how every time I increase the contour, we're moving in the same direction. They're moving in the same direction as one another. They're moving out this way. And so intuitively, we'll use that to justify this claim, to say that the gradient is in the same direction. So what I have here is the gradient of f equals the gradient of g, but because they may not be exactly the same vector, they just point in the same direction, we're saying that the gradient of f is some constant multiple of the gradient of g. Now, this is just a common value. We use this, the Greek symbol lambda. It's just a constant, but it's named after a mathematician, Lagrange, and it's called the Lagrange multiplier. So basically, again, we're saying that the gradient of f is proportional to the gradient of g. That means they point in the same direction but may have different magnitude. Its value is really not of interest. You can explore what it means from a practical perspective, and it's pretty interesting. It does have an interpretation, but we're not going to actually work to find the value. It's just sort of an intermediate step in allowing us with our computations. So why do we want to use this idea? Well, it gives us an extra equation to work with that we didn't have before, and the whole purpose of what we're doing here is that we have multiple equations with multiple unknowns, and we want to basically be able to find these unknowns to suit our constraint. So the first thing we're going to do is we are going to find the gradient vector. So the gradient of f, well, that's the derivative of, with respect to x, which we can go back a couple steps here and see that with respect to x, we would treat y to the 0.3 as a constant. So we use the power rule. 0.6 times 1,000 is 600. X to the 0.6 minus 1 is negative 0.4. Times y to the 0.3, since that's a constant, and we do a similar process for the gradient with respect to the partial with respect to y. Now we do the same thing for g of xy, but they're just constants because g of xy, which, by the way, again, g of xy is just the equation portion here, or just the left-hand portion of the equation, and this is the constant. So g of xy is set equal to this constant c. And so the derivative of 4,000x plus 10,000y with respect to x is just 40,000, and the partial derivative with respect to y is 10,000. And so because we expressed it in terms of we divided out 1,000, our gradient could just be written as 4010. So in the next video, we will connect these ideas. So let's do that next.